Thank you. I hope you can all hear me and see my screen. I will hear it if it's not the case. So yes, I was going to speak about organic solar cells, a bit different, but indeed some similarities with perovskite solar cells. I like to start with comparing the two. At least this was the situation 4 or 5 years ago. At that time, I plot here external quantum efficiency spectra for, at that time, the best organic solar cells, and at that time, the better or best perovskite solar cells. I like to compare those two because, as you can see, at the time, those two material systems had similar optical gaps, around 800 nanometer, a bit more or less. It's about 1.6 electron volt. And then you can compare the photovoltaic parameters. We already knew the perovskite has a higher efficiency than the organic. But what's the main reason now? You can see the short circuit current is similar, a bit lower for organic. This comes because in the EQE spectrum, you can see organic solar cells reach, at that time, maybe 80% EQE, but the perovskite is always 90 or even more above the gap. Fill factor is always a bit lower for organics, but not so far. But the main reason why the efficiency of the organic solar cell is lower is because the open circuit voltage is a lot lower than the perovskite solar cell. For the same optical gap, the organic solar cell loses 0.7 EV, while the perovskite at the time lost 0.5 EV. So the situation has improved or changed a bit. This is more recent. A similar comparison. Now organic solar cells have 17–18% with hopes for 20%. Perovskites are already over 25%. I just took those two from literature as an example. The photocurrent for organic solar cells, for the best organic solar cells, has increased mainly because the band gap or the optical gap has decreased with an optical gap about 1.4 EV. Perovskite gap has remained a bit the same, but there again the VOC has gone up, a high current, which makes it to 25%. So again here it's the open circuit voltage, which is very much lower than that of perovskite solar cells. More specifically, the difference between the band gap and the open circuit voltage for organics is over 0.5 EV, while for perovskite it's now in the best cases about 0.35 volt or electron volt. We will see later that this is related to the amount of non-radiative recombination. Perovskite solar cells, if you invert the process and you use them as light-emitting diodes, they are not so bad. They are with electroluminescence quantum efficiency between 1 and 10%. While if you do the same with organic solar cells, you get electroluminescence quantum efficiencies far below 1%, so 0.01% or 1 over 10,000. So you see, open circuit voltage is the big problem for organic solar cells. All the rest is getting close to what good solar cell technologies can do. So that's why it's worth looking a bit into seeing which processes occur in organic solar cells and where energy is lost. So I draw here a diagram. An organic solar cell always exists of a blend of two material, an electron donor and an electron acceptor. I schematically draw the donor as these purple lines and the acceptor as the red bolts. You excite the donor material, the exciton diffuses to the interface. The exciton splits, the electron acceptor takes the electron, the hole remains on the donor, and then hopefully the electron goes away from the hole and you can collect them. Here I draw the energy levels of all these states. This is the energy, this is ground state, so the energy of the dark. This is the excited state on the donor. This is called the charge transfer state because here the charge is transferred. But the special thing is that the electron can still fall into the hole at the interface. This is not what we want. We want to be in this state, the charge separated state, which is because of Coulomb binding probably a bit higher in energy than the charge transfer state. So what happens then if you shine light? Hopefully this process happens. And suppose then you have free carriers, but you are at open circuit. You do not extract the electrons or the holes. What will happen then? Well, these free carriers remain in the device, and if you turn off the light, they will keep traveling in the device until they meet each other, forming this state and recombine. You can also do this when you use your solar cell as light-emitting diode. So you inject charges, then you start from this state, the electron and the hole, and well, you inject the charges, the electron and hole will meet, they will form this state, and the state will decay. So if you use your organic solar cell in the forward regime, so as in a light-emitting diode, you will see emission spectra looking like this blue curve. This is old experiment, one of the first experiments when this was done. It's a blend between a polymer donor and a fullerene acceptor. The emission spectra of the pure donor material and the pure acceptor material look like this. If you blend the two and you look at the electroluminescence emission spectrum, you get a spectrum which doesn't look at all like any of those two anymore. It's completely redshifted to low energies. Plus, it's pretty difficult to measure this spectrum because it's such a weak quantum efficiency. So you have to inject 1 million of electrons to detect one photon or to get one photon out. So it's a very low electroluminescence quantum efficiency. If this process can happen, so emission from this interfacial state, so this is all emission from this CT state. You don't recognize any of the pure material. So if the emission from this state can happen, in principle, absorption should also be possible because it's the reverse transition. Physics dictate that this transition should occur. And this is indeed the case if you look at absorption spectra, but you have to look very well. You have to look with a very sensitive measurement technique over orders of magnitude. So this is a logarithmic scale, the absorption coefficient of logarithmic scale. This is the absorption coefficient of the donor. This is the absorption, the red curve is the absorption coefficient of the acceptor. And if you blend the two, you will see that there is a bit of extra absorption at very low energies. And this absorption is basically a direct transition, so absorption from the interface. So then you immediately, upon absorption, create such a charge transfer state without going through all the electron transfer processes. So that's where this absorption comes from. Now it's interesting, here is basically the same curve. We have the absorption spectrum, the blue curve. Here was the emission spectrum. Now there is a formula which relates absorption to emission. We use this formula to figure out if the emission we see comes from the same state which we see absorbing. So if the emission and absorption comes from the same state, this formula is valid. You can calculate the absorption from the emission. And you see that they match, overlap very well. So this weak absorption and this very redshifted emission, they are related to this charge transfer state. Yeah. Now it's also interesting. You can also measure EQE spectra, and you can put them on a logarithmic scale and compare them to the absorption spectrum. And you see that they look very similar. And also in this EQE spectrum on logarithmic scale, you can see at the very low energies, you can see this extra absorption band, which was responsible for this redshifted emission. You see it show up. And you can measure an internal quantum efficiency, which tells you how many electrons come out per absorbed photon over this whole range, where you can calculate it. That's EQE divided by absorption spectrum. And then you can see that even if you excite this very low energy state, so if you excite this state directly, you can create free charges efficiently as you would excite the donor directly and go through all the processes. So this CT state is not a trap state. It's an emissive state, but not a trap state. And if you end up in the CT state here, you can still generate free carriers. That's what we learned from this graph. The only pity is that this CT state is so weakly absorbing. You see, it's about 100 to 1,000 times less strong absorbing than the pure materials. So on a linear scale or in real solar cells, this very weak absorption does not contribute to photocurrent. You don't even see it on a linear scale in the EQE spectrum. But it gives us a nice tool, these type of measurements, to measure energetics of these interfacial states and measure, for example, this energy difference. This energy difference you can see as an effective gap of the material, an effective band gap. And well, if we measure now for, and this is about 100 different donor-acceptor blends, different materials. Different materials give different types of interfaces, give different types of energetics of this interfacial state. If you plot the energy of the CT state on the x-axis and you plot the open circuit voltage, that's what we were interested in because that's what's low in organic photovoltaics. You can see that they correlate, at least correlate very well. So all these different points are different donor acceptor combinations. The black ones are with the fullerene acceptors, the green ones are vacuum process, and the blue ones are with non-fullerene acceptors. Yeah, so here's a concrete example. This is not a very high efficiency system, but just to visualize it. If you blend this molecule with as a donor and you blend it with C60 as an acceptor, the frontier energy levels are like this. If you measure this sensitive absorption in the gap, you see that when you blend this molecule with C60, you get this very broad CT absorption, which is very shifted, very much shifted to low energies. And from this, from the band gap of this CT state, we can determine all these energetics, and we see that in the electron transfer process, we lose in this case almost 0.4 eV. VOC is about half a volt, and that's because we lose another 0.6 eV. So you see, from exciting the donor, we lose here about 1 eV, in part because of electron transfer and in part because of this loss. Now, if you play with the frontier energy levels of this molecule by fluorinating it, if you look here, fluorination of zinc PC shifts the energy levels down. You can also see what happens then to this CT state absorption. This absorption blue shifts, which means that the energy of this interfacial state goes up. Again, we can put the numbers on it and you see, okay, the open circuit voltage goes up because the CT state energy went up. So now the question is, if we want high voltages in organic solar cells, we need to make sure that the energy of this state, this charge transfer state, is close or equal in energy than the donor energy. So we have to play with the frontier energy levels to make them match and to get these energies as close as possible. Then we lose as little as possible in the electron transfer process. So now in the best organic solar cells at this time, we have succeeded. These energy losses have been made almost zero. So here's an example from our group where we look at interfaces between those two molecules. If we do the same experiments, maybe look on this graph, that's the easiest to see. If you measure there the absorption tails, you don't see any extra bumps sticking out or any extra absorption from CT state. The tail goes straight down. So in this case, this CT state energy is blue shifted underneath the energy of the donor and the acceptor, which means we won't have these electron transfer losses. We still, VOC is still not equal to the band gap, but that's never the case in any solar technology. I'll come back to that difference later. So now the best organic solar cells, the ones over 15%, they are all like this. They all have absorption tails straight down. They all have an energy level diagram more or less like this. The energy of the excitons is almost equal to the energy of the charge transfer state. We don't have any more electron transfer losses. But still, the open circuit voltage is still not equal to the band gap or energy of the CT state. Why is this? Well, this is true in any solar cell technology. It's never the case that the open circuit voltage is equal to the gap. There's always recombination losses. You have losses due to radiative recombinations. The radiative recombination, this you cannot avoid because every material which absorbs also emits light. So there's always a fundamental voltage loss due to radiative recombination. And then there are avoidable losses or losses due to non-radiative recombination. They are in principle not intrinsic. So people look for ways to get rid of non-radiative recombination. And you can quantify these losses by measuring your solar cells as light-emitting diodes. So you reverse the current, you look how much light they emit, specifically if you look at the quantum efficiency of emission. And you can see here, if this if the quantum efficiency of emission would be 1, the ln of 1 would be 0, then this would be 0. If you get a very low quantum efficiency, this gives a high number, and then this will be high. So here, basically I repeat this formula. So the open circuit voltage can reach a maximum value, the radiative limit, but if you have non-radiative recombination, there will always be this amount. The open circuit voltage will always be this amount less. So for OPV, I told you before, if you use OPV devices, if you use them as OLEDs, you get very low electroluminescence quantum efficiency, which means that in OPV this loss is very high. In perovskites, this loss is much lower. So the question now is, why is it so low? Why, if you use an OPV device, if you use it as a light-emitting diode, why is it such a horrible? Why is the quantum efficiency of emission so low? Yeah, so to study this in more detail, and we heard already this morning about defects. So we were also thinking, is this because organic solar cells have many defects, impurities related to the synthesis, or is it more an intrinsic property? Is it because it's due to the fact that we use organics in general? Is it so that yeah, these organic CT states always have very weak emission? So what I plot here, to figure this out, we plot here again the energy of the CT state on the x-axis, and we plot the non-radiative voltage losses we found for, again, 100 donor-acceptor combinations. We plot, so this part, so the loss part, as a function of the CT state energy. And then you see, the lower the gap, the lower the CT state energy, the more non-radiative losses we have. It goes up, there's a lot of scatter on the data, but there's a clear trend uphill. Which means that the quantum efficiency of emission decreases. So this axis is reversed and it's on a logarithmic scale. So because of this formula, you can plot EQEL and the non-radiative voltage losses, they are related. So it means if the CT state energy goes down, you have much more non-radiative recombination, and as the device as OLED gets much worse. So this seems to be a trend intrinsic to organics. Actually, if you look in the literature, the very old literature on organic molecules and emission, radiative and non-radiative recombination in organic molecules, you often see plots like this. Again, on the x-axis is the emission energy or band gap, and on the y-axis here is now the non-radiative decay rate. So the speed of non-radiative recombination. And you can see if the emission energy goes down, non-radiative recombination rates go up. For triple emitters, it's also true for fluorescent molecules. The reason, and this has been theoretically explained, the reason being the so-called energy gap law for for radiationless transitions in organic materials. So the higher the energy of the excited state, the less the probability for tunneling to a higher vibrational level of the ground state. So this is an intrinsic mechanism which intrinsically makes it that if you use low gap organic materials, you have a large number of non-radiative decay. That's also the reason why when people try to make OLEDs, it works very well in the visible where the gaps are high, around 2 eV, but then when you go below 2 eV or the range of 1.5 eV or even lower, you can see that EL quantum yields go down. So it's very hard to make OLEDs in the near infrared for this reason. Well, our solar cells, they're all emitting in the near infrared because that's where the optimum gaps are. We want to collect a lot of photocurrent, so we want low gaps. But the consequence is that we have low emission quantum efficiency. So here's this graph again, the effective gap of the organic solar cells and the non-radiative decay rate. You can, this doesn't matter which acceptor you use. You use a fullerene acceptor, a non-fullerene acceptor. It doesn't really matter which material. You always see a very similar trend with a lot of scatter. So if you look at this graph, you could think, and if your goal is, well, let's decrease these non-radiative losses, you could say, well, let's look at very high CT state energies in the visible, because it looks, if you go to high CT state energies, the non-radiative losses should, according to the trend, go down. So this is what we did. We looked at now at donor acceptor blends with a high CT state energies. We're here around 2.5 EV. Normally, this is not where you would make solar cells with such high gaps, because they don't absorb any, or they don't absorb much sunlight. We're in the blue region here. But you do see when we look at those, when we look at donor acceptor combinations in that region, we will have low non-radiative voltage losses and okay EQE-EL. So EQE-EL is in the range of 1 to 10%, at least in the best case. One example here is this material combination, the donor acceptor combination. This is the donor, this is the acceptor. You can see we can get, in this case, VOCs over 2 volt, 2.05 volts. With a CT state energy of 2.5 volts. So again, here we have about 0.4, 0.45 EV voltage losses, which is much lower than the typical 0.6, 0.7 voltage losses. So we have severely reduced non-radiative recombination here. This particular device is a solar cell, which absorbs blue light only. And when you drive it in the forward regime, it emits light, yellow light in this case. So what we learned from this graph is it is possible to get low non-radiative voltage losses in the same range as perovskite solar cells, but we can only do this for very high gap organic materials, not for low gap organic materials. This is basically the same graph. Here is this energy of the CT state. This is the upper limit for the open circuit voltage, this black curve. That's the Shockley-Queisel limit for the open circuit voltage. If the gaps are in the range where we want them to be for a lot of sunlight absorption, you see there's a considerable difference between the two. But if we increase the gap, you can see that the VOC get closer and closer to the upper limit, the Shockley-Queisel limit for the open circuit voltage. So it's a bit unfortunate for organic solar cells that the sun emits mainly in the near infrared and not in the visible, because in the visible organic solar cells, for any visible light sources, energy conversion with organic solar cells would be very efficient because there's not much voltage loss there. This is what I just showed you, those visible light emitting PV cells. So here is again the voltage, the non-radiative voltage loss of organic solar cells. Here I compare it to then the better efficiency technologies. You can see here perovskites have very low non-radiative voltage losses, gallium arsenide and silicon also. With the organics, we can't reach it in the region where the optimum gaps are for sunlight, but we can reach them, yes, in the blue UV light region. So here this is my second to last slide. So to understand if we can get efficiencies which are comparable to those high efficiency technologies, we want to know, of course, can we reduce these non-radiative voltage losses, but at optical gaps in the 1.5, 1.6 EV region. So we try to model. We know now, okay, one of the main reasons why organic solar cells have low voltage losses is because of this intrinsic energy gap law, this non-radiative decay via molecular vibrations. So instead of emitting light, the molecules start vibrating. And we can model this, and with some assumptions, we can calculate a lower limit for what we think we can, a lower limit for energy dumped into vibrations, so a lower limit for non-radiative voltage limits and an upper limit. So how to get to these low limits, which molecules to design, which have low non-radiative decay rates, and where it's difficult to dump the energy into molecular vibrations. These are probably very stiff molecules. Theoretically, we can make them, but practically that's another issue. So that's the blue curve. So we do think that at these gaps we can go down, but it will not be easy. At these gaps decrease the non-radiative voltage losses. future research should, if we want to improve efficiency of organic solar cells, we should understand these internal conversion processes and all these vibrational modes of these organic molecules, because that's what's currently limiting the efficiency at open circuit voltage. But anyway, suppose we cannot solve this problem, and suppose that we're always that our non-radiative voltage losses and our VOC losses are always in the range which they have been. I've drawn here two lines, like an average limit and a lower limit of these non-radiative voltage losses. If you put this into a model, you assume that you can get the same quantum efficiencies, external quantum efficiencies, photovoltaic external quantum efficiencies as perovskites, and similar fill factors which have been reached in organic solar cells, then it should be possible to reach power conversions efficiencies over 20% for OPP, even if we do not solve this non-radiative decay problem. So here is plotted the Shockley-Queisser limit that assumes no non-radiative voltage losses at all, quantum efficiency 100%, fill factors 90%. If you make similar assumptions, but you can accept non-radiative voltage losses as they are here, then we should still be able to get over 20%. So this was my last slide. Thank you for your attention, and I'm open to any questions, probably in the question session.